Okay, let's look at something that's a bit more involved. In a recent video, you learned how to calculate percent composition by mass. And then you've also learned how to tell the difference between molecular and empirical formulas. So let's put that all together and we can calculate formulas based on the information that we learned from percent composition by mass. So for in this example, we say dichloroethane. It says it's a compound that's used for dry cleaning. It contains carbon, hydrogen, and chlorine. So we know what it is made up of. It has a molar mass of 99 grams per mole. Analysis of a sample shows that it contains 24.3% carbon and 4.1% hydrogen. So we want to know what is the molecular formula and what is the empirical formula. So let's start with what we know. I wrote off to the side 99 grams per mole. We know that it's going to add up for that for its molar mass. We know that carbon makes up 24.3%. We don't know the subscript just yet, but we know that it is 24.3% by mass. Hydrogen makes up 4.1%. That was given to us. Notice that chlorine, it told us it had chlorine, but it didn't tell us what the percent composition by mass was. But that's something that's easy. We know that all of the mass has to add up to 100%. If carbon is 24.3% of that 100, hydrogen is 4.1% of that 100, what is left over? In this case, you do your math, 100 minus 24.3 minus 4.1. We are left with chlorine being 71.6% of our mass. So let's continue with what we can calculate. So again, let's just assume that we have 100 grams of whatever this compound is. If we assume that we have 100 grams, then all of a sudden that 24.3% of carbon, we can just say it is 24.3 grams of carbon. We multiply that by 1 mole, which is 12 grams of carbon. Again, this is something that you get from your periodic table. Make sure you're referencing that to get your molar mass for each element. So we do our math there and we get that we have 2.025 moles of carbon in this compound. Our next one, we do the same thing. We assume that we're working with 100 grams. So that 4.1% of hydrogen is 4.1 grams of hydrogen. Our periodic table tells us that 1 mole of hydrogen should weigh 1 gram. So we get 4.1 moles, and that should say moles actually. Let me go ahead and correct that. Should say moles of hydrogen. And notice that MOL, it's the shortened version of mole. So that's just where I got that. And then our last one, that 71.6% of chlorine that we calculated, we'll say that it's 71.6% or 71.6 grams of chlorine, sorry. And we know 1 mole of chlorine is 35.45 grams according to our periodic table. So what we've done now is we've calculated how many moles of each of those that we have. Notice those numbers, they are pretty close to whole numbers. This 2.025 is almost 2. 4.1, almost 1. 2.02, again, almost 2. This isn't perfect, but we can at least try to figure out if this is what we get. So for example, if I say that I have 2 moles of carbon, if I think that subscript should be 2, I'll do 2 times that molar mass for carbon, which is 12, plus 4 for hydrogen times the molar mass, plus 2 for chlorine times that molar mass, and it should add up to the total, which they told us was 99 grams per mole. Notice I get 98.9 grams per mole. That is almost exactly what I wanted, so I can assume that that is correct. So, because that is so similar, I can say that C2H4Cl2 would be my molecular formula based on my calculations. Notice that I can simplify that in order to get my empirical formula. I can divide it by 2. So CH2Cl is my empirical formula. So it takes a little bit longer to do these calculations, but it is possible and it is something that chemists will experience when trying to determine what a compound is made